Alan Carter is a professor in construction engineering at the Department of Engineering Department at Ecole de Technogie Supérieure in Montreal. Alan is responsible for the pavement and bituminous materials laboratory at the school. His research is focused mainly on cold recycling bituminous material, thermobiological characterizations of bituminous materials, surface treatment, and mechanistic empirical pavement design. So Alan will talk to us about in-place recycling research to improve construction and performance. Please join me to welcome Alan.
Bonjour. Don't worry, that's the only French you'll get. Okay. There's only 2 French Canadians here, and so okay. I'll try to be as brief as possible, so not to keep you away from the coffee. I'm pretty sure there's coffee in the coffee break, but just improving. In-place recycling research to improve construction and performance. The different speakers before me actually showed different aspects of cold recycling. And basically, I think everybody here, we agree. Okay? It's good stuff, we should do more. Okay? That's fairly easy. So I don't think I need to convince anybody here. But in most conferences where I go, where I teach class and stuff like that, I always have to convince people that it's actually good stuff, that it will last. It does last, right? But it's a sensitive subject. I don't remember who said this morning that construction industry doesn't want to change. There's a bunch of contractors out there, they've been doing the same hot mix or something for the last, I don't know, many years, and that's working. I'm not doing anything else. Okay. Right? Some of them actually really want to try something, but then they propose that to whatever, a DOT or something like that. They say, hey, no way. Can you prove without a doubt that it will last as long as the other one? No, it's called a test section. Right? So who's going to pay if it fails? You. I'm the university guy. I don't pay for anything. Okay? So I get paid to basically break the roads of everybody else. Okay? And cold recycling, yeah, we still have to do stuff like this. And depending where we are, right, in Montreal, in Quebec itself, yeah, we have a bit colder temperature than the sunny California we're in right now. Okay? So we do things a little bit different. But I have friends, like, let's say, in Brazil, where they do cold recycling, quite a lot, actually. But in their regulation, they're not allowed to leave it open to traffic. So when they do cold recycling, they do hot mix on top of it the same day. So they close it at night, they do cold recycling, as soon as it's done, hot mix on top. Okay? So they're cooking it. So it's a somewhat cold cooked recycling. Right? So there's a bunch of things like that we need to talk about. So this is the outline of my presentation, so I'm going to talk a little bit about performance of cold in-place recycling. Talk about the evolutive behavior. Okay, I'm going to concentrate a little bit of field, but I'm going to talk mostly about lab stuff. And I'm going to show you the RILEM Interlaboratory Program. So RILEM, it's a big association, and we're actually working together a bunch of different labs, a bit everywhere around the world, on this. So which lab, what were we going to do, and a summary of this. The first thing is names, definitions. Right? For most people, they say it's CIR and FDR. Like, I'm sorry, but CIR, it's a technique. It's not a material. Right? If you want to be precise, you can have CIR material, FDR material. Okay, but CIR is a technique. And not all the CIR are the same. And then what happens if I put foam? But if I put emulsion? If I put cement? I put a lot of cement. I put a lot of cement. Okay? Yeah, I almost said something I should not. Okay? You want to put lime. So what are the names of this? Okay? So this is a proposal that was done in one of my friends in Italy. Basically, CBTM in the middle. Do we have? Yeah. Okay. CBTM in the middle. Cement bitumen treated material. Right? And then you put more bitumen, you put more cement. How much is too much? Who knows? Okay? So you'll see a lot of people say, okay, you have to put less than 2% cement. Okay, that exists. They say less than 3. You go in South Africa, they say at 0.5% cement and more, you start to have kind of a brittle behavior. In Italy, they can put up to 6% cement. It all works. Every single one of them. Okay? In Quebec, okay, you all know where Quebec is. Okay? Good. Okay? Far. Okay? Okay. So not only we're the annoying French Canadian, but we have a big road network. Okay. So MTQ is the DOT, basically around 33,000 kilometers of highways and stuff like that. Municipal law, all right. Okay. Roads about 92,000. We're only 8 million people. Okay. So big network, not a lot of people. And we've been doing cold recycling for, I don't know, like 30 years now. Okay? And cold recycling on highways, low volume, anything. Okay? Any of you actually landed in Montreal airport? Nobody went to Montreal? Come on, Montreal's a nice place. Okay? We don't bite much. Okay? The base course of the Montreal airport, it's cold recycling. Right? And it's Eurovia who actually did the job, and they have a blast to show the big, I don't remember the number, you know, the biggest jumbo jet that lands on it. And okay, it's perpetual pavement, like it was just mentioned. So if we look at the evolution of what was done, so the green line would be FDR, the purple-ish line would be CIR, and the blue line would be FDR, but treated. The green line, basically something we should not do, okay? But it's popular, because we're just recycling it, putting it down, compacting it and everything, but we do not put any treatment. No emulsion, no foam, no cement, no lime, no nothing, okay? It becomes a granular base. It's a very bad idea, okay? But it's a popular, cheap idea, but bad, okay? Because most of the time, it basically becomes a granular base that has lower quality than virgin aggregates. Because there's bitumen in there that looks like a lubricant, okay? So if you look at CBR values, something like that, it's not as good. So it seems to go pretty, you know, it's more and more. But it basically stopped there, okay? So it went up, and then it kind of stabilized and going down a little bit. Okay. Why? Nobody's sure. Okay. If you talk to contractor, you talk to the Miller Group and everything, they would like that to go up. But okay, we're kind of stalling right now. How does it fail? Depending who you talk to, some people will say, oh, it rots. There's rotting problem. And it's easy to understand, you know, there's 10, 12, 15% air voids in those, so it's normal. Oh, it's not rotting, it's densification or something like that. Permanent deformation. Nah, it doesn't. Okay? If we look at most data that you have data here, there's a bunch of other data a bit everywhere, it doesn't rot. Okay? Here we're talking about 5 millimeter rot depth. Millimeter, it's small. Okay? The metric thing again. Okay? So there's 25.4 millimeter in an inch. The 0.4 is very important. Styrene is expanded asphalt, it's foam. Okay? Then this is another physical condition index. It's kind of, can I back up? Yeah, I can. Okay. So physical condition index, it's kind of a pavement condition index, if you want. Okay. And if you put, those are all cold recycling, but if you put hot mix beside it, it follows exactly the same trend. Okay. And this one is in Quebec. Basically, every single red line is a different project. Okay. And you look at IRI, yes, in metric again, okay, in meter per kilometers, and a good value. Basically, on the highway and everything, you have to be below 2.2 or something like that. Okay, so somewhere here. And it behaves pretty well, right? And no, it doesn't fail in rotting or fatigue or something like that. Okay? How does it fail? We still don't know yet. Nobody is able to give you a very precise definition of the failure mechanism of those materials. If it's a granular material, okay, it cannot fail in fatigue, because granular material doesn't fatigue. Okay? There's no cohesion or anything like that. If it's a cohesive material, something that's holding together and everything, you need to have bitumen everywhere. Okay? But bitumen, binder, whatever binder it is. Do we have binder? You'll hear people, and it was mentioned just before me, like a half-bounded material, okay? But it looks pretty black everywhere. Okay? We're in between. Okay? In South Africa, if you hear Kim Jenkins say, he will say that basically it's a very, very good aggregate source. It's kind of a plus-plus aggregate source. And other people will tell you it's kind of a weak HMA. Okay? So we agree it's not an HMA and it's not granular. Okay? They were somewhere in between. This is a very interesting study. So this is in the States. There's a few of those data points that come from Canada, from Ontario, in fact, that show dynamic modulus. So to give you an idea, at 10 hertz, 21 degrees Celsius, hot mix would be around that yellow line. I say, hey, it's very good stuff. So we actually have CIR, you see you have CR and FDR there, that are almost, if not, there's an outlier there, okay? If not stiffer, that's not even possible, okay? That would be awesome. So you have data points that basically says that it's the same as a hot mix in terms of stiffness. You have to be very careful with data like this, okay? Because this is a snapshot. It's one frequency and one temperature. One thing that we know is that if you look at different temperature, different frequencies, those materials are not as thermal sensitive or frequency sensitive as hot mix. It's mostly like a flat line. So if we look at this, okay, you have the HMA line, which is very sensitive. So if you look at temperature, or you could look at frequency if you want, okay? So low temperature could mean high frequency, and high temperature, low frequency, okay? It's the same, temperature per superposition principle. So what you see there is that the red line, the hot mix, there's a steep slope. Everything else, not as much, okay? So if you look, for example, I take that here, if I look at high temperature, hey, it's much stiffer. If I look at low temperature, it's a lot worse. Okay? So it depends what I'm looking at. So we should really look at the full behavior. But again, if it's a granular material, it's a perfectly flat line. And it's not a perfectly flat line. Okay? So we know that there's an impact in there. Something else that was mentioned is the cement quantity that we put in it. How much cement do we want to put? If you talk to the suppliers, the cement suppliers, we're not putting enough. Okay? Okay? FDR 100% cement, CIR 100% cement does exist. Okay? And it does work. Okay? I believe, exactly like it was mentioned before, that there's no universal binder for all those mixes. We do need to do a study to verify which one is which. Okay? Of course, some companies do prefer some product. For example, lime is not that popular depending on which region you are. And some will say it's just because it makes a mess. Okay? It does make a mess. Okay? So, for example, those are some of my results. So you have SCB test. SCB, it's a cracking resistance test. Okay? It's already cracked, and we see how resistant it is to crack propagation. So if you put more cement, the more cement you put, in this case we go up to 5% cement, okay, the stiffer it becomes. But if we look at the slope of this, okay, it becomes more brittle. Good. it kind of makes sense. More cement, more brittle. Now, what's the limit? We don't know. Right? This is brittle. Okay? We need more results. Okay? But that can give you an idea. And actually, to say that 5% cement makes it a more brittle mix is not even a good thing. We should never say, okay, 2%, 5% is too much, is not enough. We should use a ratio of the hydraulic binder versus bituminous binder. Because if you put 5% cement, but you put 5% bitumen in it, okay, maybe it's not brittle at all. Okay? Something that we need to be really careful with, it's the evolutive behavior. Okay? You all know, I think most of you went on job sites and everything, okay? The milling speed depends on the thickness, depends on the machine, depends on the operator and everything. Some operator will tell you, how fast can you go? As long as it doesn't start to jiggle and jump, you're good, okay? Not a nice thing to do, okay? Because the speed has a direct influence on the gradation of your whatever material that's after, okay? So you have to be careful. Depending where you are, regulations and everything, one of the really nice advantage of this method compared to others is that you can open it to traffic really quickly. Okay? 500 meters behind it, it means that within an hour, it's open. Okay? Is it cured? Nah, not remotely. Okay? So some people tell you, that's why we use foam. Foam, much less water, and we don't have a problem with that. Okay. Okay? In Quebec, basically, when you have a contract, it's not mentioned foam or emulsion. Cheapest one wins. That's it. They're considered totally equivalent. You can agree or disagree with that. That's the way it's meant. Okay? So, we can open it really quickly. Really quickly. It's filled with water. Some water went out of it, some, okay? Some is still in it. It's an emulsion. If it's an emulsion, of course, it's not cured, it still smells and everything, okay? It's not a problem. But we do open it to traffic. Someone this morning said that sometimes in construction, it's basically the construction that is the worst part. So how are we supposed to test this if I'm not able to core it? Okay, because it's some of those materials, we go the next day, we try to core it, and nope. Some of them, you go an hour after, you core it, and yeah, okay. So, but do you want to take chances? Usually, DOT and others, they don't like us to transform their road in Swiss cheese, right? It's awesome. We want to do that. And I want to do coring in the wheel path, right? I mean, that's where the information is, okay? So one of the things that we developed, that we're working on, is basically a non-destructive testing. It's by wave propagation. But wave propagation exists for a long time. I know. But it's filled with water. So compressive wave doesn't work. So you have to use shear waves. And depending how you analyze the data will give you different results. So this is one of the devices that we're setting up right now at ETS. That's the name of the school. And it actually works pretty well. And with this, we can actually see, without going too much into details, the yellow dots that you have there, it's the water loss. Okay? And we know that the stiffness is related to the water loss. Not only stiffness, there's indirect tension, modulus, stuff like that. Okay? And we go with the shear velocity and water loss and the stiffness, and we get a pretty good relationship. Okay? It's basically linear. Okay? So you see here, so this is the evolution of the shear waves. And the yellow one is the water loss. So you see those two lines are parallel, so it's fairly easy to make a relationship in between those two. Okay? Then we'll be able to see what kind of stiffness I have, what kind of behavior I have, before it's stiff enough to be tested the normal way. The evolutive behavior does change over time. This is wave propagation, but compression wave, because we wait that it's fully stiff. It's very high stiffness, because instead of being at 10 hertz, we're at like 120 kilohertz, okay? Because wave propagation. But we see that it does increase with time. But there's a lot of studies that actually show that after a while, it goes back down. The optimal stiffness seems to be, if we look at most of the job site that we look, after like 3 years. Then why does it go down? Right? And does it go down significantly? Not that much. Okay? So first, there's degradation, of course. Right? Like hot mix, like any material, it's possible. There's aging. Does it age? It's pretty well covered. Right? Usually we put whatever on top, hot mix, warm mix, micro, something on top. So there's no air that goes there and everything, so it should not age too much. Okay? If it starts breaking, the modulus actually starts to go down much faster than this. So why does it do that? So far, not a clue. Okay? But we've seen many, many job sites that it's the case. ARA is a very nice organization. There's a bunch of very nice organizations that try to have people work on this. RILEM is one of them. Who here knows RILEM? Okay, not many. So RILEM is like a, I think it's 75 years old association, okay? Mostly in Europe. There's, I think right now, close to 1,500 members. Okay? So it's a fairly nice association. Okay? All voluntary, so that's the tricky part. And it's separated in 2 different clusters. The biggest clusters are for concrete. There's more people working on concrete than asphalt. But the nicest clusters, of course, is cluster F, okay? On bituminous material and polymer. In that cluster, there's the 264 wrap, and in that one, there's 5 TGs, without going in details, okay? But it's cold recycling, hot recycling, LCA, asphalt binder, etc., etc., okay? The most interesting one, of course, is cold recycling, okay? I'll wait. Good, he took his picture. So, cold recycling. So for the cold recycling, I'm in charge with one of my colleagues of the TG1, and those are the actual actively participating labs that work with us. Okay, there's more labs than that, but a bunch of them just come to meetings or, you know, the free beer, open bar, and stuff like that. But the lab work, not that much. Okay.